In this video, we introduce our work, titled Subnet-Aware Dynamic Supernet Training for Neural Architecture Search. Neural Architecture Search, or NAS, aims to automatically find an optimal network architecture from a given search space under hardware constraints such as flops or memory. In recent years, NAS has become a practical alternative to manual design, especially when targeting diverse deployment scenarios. To reduce the cost of NAS, sampling-based NAS methods have been proposed. These methods leverage a supernet that encompasses all candidate subnets in the search space. In these methods, the supernet is trained by iteratively sampling a single or multiple subnets. The weights associated with the sampled subnets are updated using forward and backward passes. After training, the supernet is used as a performance predictor to evaluate and rank candidate subnets, enabling efficient architecture search without retraining. Despite their success, existing methods adopt a static training strategy, applying the same learning rate schedule and optimizer to all subnets. This is based on the assumption that all subnets can be converged to same level if they are trained with the same setting. This overlooks the fact that subnets have diverse structural and computational characteristics from each other, and thus they should be trained in different settings. We identified two key issues in static supernet training. First, it causes an unfairness problem, where the supernet training is biased towards the low-complexity subnets. Considering high-complexity subnets have more parameters to learn compared to those of low complexities, high-complexity subnets require more training amounts for accurate ranking. Discarding this difference in the supernet training process places the rank of the high-complexity subnets behind the low-complexity ones, even when they might be supposed to provide better performance. Second, sharing a single optimizer for all subnets causes a noisy momentum problem. That is, the momentum storing the running mean of gradients becomes noisy due to varying gradients across the subnets. Generally, exploiting a momentum in an optimizer stabilizes the training process as it mitigates oscillations of network parameters by using the historical gradients. However, in the case of the supernet, the gradients come from diverse subnets within the search space, and they can vary significantly. To address the problem, we propose a dynamic supernet training framework that exploits distinct training strategies adaptive to individual subnets. First, we propose a complexity-aware learning rate scheduler that alleviates the unfairness problem for the subnets. Specifically, considering the number of parameters to tune for each subnet, we slowly decay LR of high-complexity subnets to encourage more parameter updates while we accelerate the LR decay for low-complexity ones. This enables a more balanced training of each subnet according to its complexity, alleviating the ranking inconsistencies. Second, we present a momentum separation technique that stabilizes the supernet training process. Motivated by the observation that the subnets with similar structures provide similar gradients, we cluster the subnets based on the structural characteristics and use a separate momentum buffer for each cluster, stabilizing the momentum updates. Please note that we still use shared weights across all subnets, suggesting that the overall search time remains the same. Note also that memory overheads for additional momentum buffers are negligible compared to those for forward and backward passes. We validate our approach on NAS Bench 201 using CVPR 10, CVPR 100, and ImageNet 16 to 120. We integrate our method into three representative NAS frameworks: SBOS, FAIR NAS, and FS NAS. Across all settings, our method consistently improves both ranking consistency and top 1 accuracy with negligible overheads. Furthermore, our method provides superior search time accuracy trade-off compared to state-of-the-art methods. We further demonstrate the scalability of our method on the mobile net search space. We apply our method to SBOS, FAIR NAS, and FS NAS under multiple flops constraints. Our approach consistently improves the performance of retrieved subnets. This confirms once again that our dynamic supernet training technique can be an effective alternative to the static one. In summary, we identify two limitations in static supernet training: unfairness and noisy momentum. To address them, we propose a dynamic training strategy that consists of complexity-aware LR, scheduler, and momentum separation. Our method is simple, efficient, and compatible with various NAS frameworks and search spaces. Extensive experiments demonstrate that our approach improves performance and ranking reliability while incurring little additional cost. Thank you for your attention. For more details, please visit our project page.